Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh dan salam sejahtera kepada semua pelajar elektrik Circuit 2 BEV 10403. Okay, so today we will discuss about sinusoidal steady state analysis. Okay, chapter 4, which is our subtopic actually is equivalent impedance and phasor analysis. Okay, so this is learning outcome of this topic. So at the end of this chapter, you should be able to apply phasor concept in AC driven circuit analysis. Okay, number two, you can apply the phasor IV current and voltage relationship of the resistor, capacitor and inductor in steady state circuit analysis, AC circuit analysis. And number three, you will be able to apply the equivalent impedance concept rule to find the magnitude and phase relationships of currents and voltages in AC circuits. And then the last one, you will be able to draw phasor diagrams for the circuit voltages and currents. Okay, this is the main contents of this subtopic. Okay, first of all, we will discuss about introduction of this subtopic, and number two, we will review, we will recall back our previous concept, which is Kirchhoff voltage law that you already studied in electric circuit 1, if I'm not mistaken. Okay, number two, Kirchhoff current law, KCL. Okay, these two voltage and current law basically is important in circuit analysis, either in whether in DC circuit analysis or AC circuit analysis. Okay, then impedance combination, series connected, impedance combination, parallel connected, and then the last one actually is how to apply all these theorem and impedance concept for the phasor analysis. Okay, introduction, phasors and circuit analysis. Okay, so in previous topic we already discussed about phasor. Okay, this is a summary of voltage current relationship, okay, between circuit element. Let's say we have a R, L and C. So in time domain, how to determine voltage across R? Okay, V. Okay, in time domain, our V basically is small v. Okay, small v equal to R times I. I also small I, current. Okay, this is in time domain. But in frequency domain, how to write voltage across resistor in frequency domain? We need to write V in capital and I in capital. Okay, V equal to R times I. Okay, for element L, inductor, this is an inductor. Voltage across L in time domain, I think you already we already discussed in chapter 1 or 2 if I'm not mistaken. Yeah? Okay, V equal to L di over dt. This is in time domain. In frequency domain, V equal to J omega L times I. J omega L equal to Z, impedance of L. Okay, in frequency domain. Okay, similarly to C, okay, we have I current equal to C dV over dt. We need to differentiate V over dt. So in frequency domain, we can determine voltage across C equal to 1 over J omega C, which is equal to ZC times I. Okay, so basically in this subtopic we will use frequency domain either in phasor form or in rectangular form to analyze our AC circuit. Cool. So to use phasor circuit analysis, we first need to know how KVL, Kirchhoff voltage law, Kirchhoff current law, KCL and Ohm's law apply in phasor domain. Okay, so today we will discuss about KVL, KCL and Ohm's law in detail. Okay, so second we try to review about impedance. Okay, impedance which is Z for the circuit elements. Okay, in the previous lecture, we already discussed how to prove the impedance for the circuit element. For example, let's say we have R, okay, circuit with R and voltage source. So how to determine impedance for R, for resistor? So Z, impedance basically is Z, so Z equal to R. So in this case, we call it ZR equal to R, the value of R itself, which is in unit ohms. Okay, let's say we have a L, okay, L. So what is the impedance of ZL? ZL equal to J omega L. Okay, or in other words, we can write JXL. In this case, XL equal to omega L. Omega equal to 2 pi times frequency, 2 pi F times L. Okay, for C circuit, okay, circuit with C elements, okay, let's say C component, we have a C, so Z equal to, ZC equal to 1 over J omega C, omega equal to 2 pi F, okay, frequency, F is frequency, or equal to minus J. Why minus J? Because 1 over J equal to minus J, okay. Please bear in mind 1 over J equal to minus J. Okay, XC. In this case, our XC equal to 1 over J omega, 1 over omega C. Okay, so or we can write Z equal to 1 over Y, admittance. Okay, Y over 1, which is admittance. Okay. This is a review for impedance of the circuit elements. Okay, next we look at to Kirchhoff voltage law. Okay, what is Kirchhoff voltage law? Okay, Kirchhoff voltage law in the phasor domain. Okay, let's say consider we have a circuit. Let's say we have a voltage V1. This is a positive. This is the negative polarity of the voltage source. Okay, V1, and then we have a load. Let's say load. Okay, so the positive, negative V2, and then we have a load 2, positive, negative, okay, V3, and so on. Okay, so this is a voltage across, let's say, load V2, V3, and until Vn. So, can you recall your Kirchhoff voltage law, the concept of Kirchhoff voltage law? Okay, so try to recall your KVL. Okay, recall that KVL states that the sum of voltages around a closed path, this is a closed path, closed loop, is equal to 0. Okay, based on the circuit above, okay, we can analyze, for example, really use pen. Okay, you can analyze this loop, you can analyze this loop, for example, you can analyze this loop, okay, by using this direction, for example. Okay, so first meet a negative, so minus negative V1 T, and then we meet plus, okay, plus V2, and then we meet positive, and then we plus V3 and plus Vn equal to 0. This is the equation of the time domain equation for Kirchhoff voltage law. Okay, so in order to perform the circuit analysis in AC steady state analysis, we need to use the phasor domain or frequency domain. Okay, KVA. So what we can say that KVA is also applies in phasor domain as well as in time domain. So in order to perform the circuit analysis, okay, basically we use the phasor domain. We use a phasor domain, which is easy to perform the circuit analysis. Okay, we use a phasor domain. Okay, this is the similarity between time domain circuit and phasor domain circuit. This is the KVL for time domain circuit. Okay, similarly, when you convert from time domain to the phasor domain, so of course your VT time domain become V, capital V. Okay, please bear in mind in phasor domain, either in polar form and so on. So your notation for voltage, current and Z should be capital. This is a V1, this is a V2, V3, and Vn. Okay, the polarity actually is still same with the time domain circuit. Okay, similarly, if you apply the KVL, let's say for this loop, you apply the KVL. Okay, so minus V1, let's say minus V1 plus V2 plus V3 until Vn equal to 0. Okay, equal to 0. Or you can write V1, you start with the output. Okay, let's say positive V1. Okay, and then output is minus, so minus V2, then the output is for V3 is minus V3, and then minus Vn equal to 0. Okay, you can choose either based on the first step or using for the first approach or second approach. Is up to you. Okay, that's the important concept, which is KVL, Kirchhoff voltage law, that you have to understand. Okay, number 2, okay, concept of Kirchhoff current law. We call it KCL. Okay, we call that Kirchhoff current law state that the sum of current leaving or entering a node actually is equal to 0, which means that, let's say we have a circuit. Okay, let's say this is the node. Okay, one node. Okay, this is our one node. Current enter to the node basically equal to current leaving the node, or in other words, sum of the current enter and leaving in a node equal to 0. Let's say you have a IT. This is a I1 across, let's say, Z1, I2 across Z2, for example, and IN across Zn, for example. Okay, so how to write a KCL? So I, current enter, basically we use a positive notation. Current enter, we use to the node, we use a positive notation, positive. Okay, this is a current leaving minus I1. Okay, let's say minus I2, current leaving to the node minus IN equal to 0. Okay, is it clear? Or in other words, you can write that current enter equal to current leaving. Okay, that's all for KCL. Okay, so you have to really understand, KVL and KCL. Okay, so for time domain, let's say the summation of current enter equal to current leaving. Okay, for time domain. Similarly, for phasor domain, you can write in phasor form. So first of all, you have to transfer from time domain. This is IT, I1, I2, and IN. So you can write I. Okay, this is basically is capital I. This is capital V, I1, I2, and I3. Okay, so KCL for phasor domain circuit. So I1 capital I minus I1 minus I2 minus IN until n element equal to 0. Okay, same for time domain or for phasor domain. The difference actually how we write the notation for current and voltage for time domain. Okay, we need to use capital letter. For example, this one, current. Okay, so that's all for KCL and KVL, the review of KCL and KVL for AC circuit analysis. Okay, next we move to impedance combination. How to determine impedance for series connected circuit. Okay, let's say we have a circuit V and we have a load. Okay, Z1, Z2 until Zn. Let's say voltage across Z1 equal to positive V1, V2, and Vn. Okay, so by applying KVL, by applying Kirchhoff voltage law, this is a KVL, Kirchhoff voltage law, okay, to the circuit, summation of voltage equal to 0. So therefore we can write, okay, for this loop, for example, we have this loop, okay, minus V plus I times Z1 plus Y plus, this is a positive, plus at the load, because load consume we have a voltage drop here, okay, plus IZ2 plus IZ3, for example, plus until IZN equal to 0. So equivalent impedance at the output terminal, okay, impedance Z seen from here, from the output of the from the input of the terminal, okay, let's say we call it a Z equivalent. So we know that Z equal to V over I, which is summation of Z1 plus Z2 plus Z3 until Zn. Okay, in series. This is a series connected. Okay, so look at to example number 1. Okay, determine the number. Okay, determine the total impedance of the circuit at a frequency of 40 kilohertz. Okay, let's say we have a supply frequency, a supply source, supply voltage with frequency of 40 kilohertz. Okay, connected to the C, okay, capacitor and resistor in series. So what is the total impedance? What is the Z total? What is the Z total? Okay, Z, let's say Z total. What is the Z total? Okay, same from here. Okay, series circuit. Okay. Okay, first of all, you need to convert from, this is a time domain because we given value of C and R. Then you need to convert to the phasor domain, which is C, you convert to ZC. You need to determine ZC. R, you need to determine ZR. ZR equal to R. Okay, 25 ohms. ZC equal to 1 over J omega C. Okay, 1 over J omega C or minus JXC. Okay, 1 over J omega C, give omega equal to 2 pi F. Okay, this is a 2 pi F times C. Then you will get this one. Okay, this is ZC. So if you have a circuit in series, so Z total equal to ZR plus ZC. In this case, ZR equal to 25 plus ZC equal to minus J19.89 ohm. Okay, this is your total impedance. Okay, you can write in rectangular form. This is in rectangular form, or by using your calculator, you also can display your answer in polar form. Either one, it's up to you, or depend on the question. Okay. Okay, next, let's say we have a impedance combination in parallel. Okay, let's say we have a current source here or voltage source here, and then we have Z1, Z2, Z3, let's say until Zn connected in parallel. Okay, this is connected in parallel. Okay, connected in parallel. Okay, so voltage across each impedance is same. Okay, voltage across impedance Z1, Z2, Z3, let's say, and Zn basically equal to 1. Okay, because voltage across the same node actually is same or equal to Vn in this case. Because by applying KCL, Kirchhoff current law, current enter equal to current out, or summation of current enter and leaving equal to 0. Okay, in this case I write current enter equal to current out. In this case, current enter equal to enter to the node equal to I. Okay, I equal to current leaving I1 plus I2. Let's say we have I3 plus I3 and until IN. So we know that I1, how to determine I1? By using Ohm's law, V over Z1. I2 equal to V over Z2. Similarly to V as IN equal to V over Zn. So when we simplified this equation, we have a same voltage, okay, V times 1 over Z1 plus 1 over Z2 until 1 over Zn. This is become our equivalent impedance. This is become our equivalent impedance. So the equivalent impedance is 1 over Z EQ, commonly this is the equivalence, okay, equivalence impedance equal to 1 over Z1 plus 1 over Z2 plus 1 over Z3 until 1 over Zn. This is impedance. So admittance, okay, what is the definition of admittance? Okay, previously we already discussed about admittance. Admittance equal to, okay, the unit of admittance. What is the unit of admittance? Siemens. Okay, y over z. Y over z equal to y, so we can write y equivalent equal to, okay, y1 plus y2, because y2 equal to 1 over z2 until y of n. Okay, admittance actually is inverse of impedance, inverse of z. Okay, is it clear? Okay, so let's say we have two impedance connected in parallel. Sorry, this is connected, okay, wrong, this is a parallel, connected in parallel. Okay, connected in parallel. So so what is the total z? 1 over z equivalent equal to 1 over z1 plus 1 over z2. Or we can write z equal to z1 times z2 over z1 plus z2. Okay, you just solve this mathematical equation, okay, for z, and then you will get this equation, z equal to z1 plus times z2 over z1 plus z2. Okay, so the equivalent impedance of z1 and z2 in parallel, okay, you can redraw the equivalent circuit, okay, V and Z equivalent. Okay, is it clear? All right. Okay, so we can show that the n parallel connected admittance in the circuit below can be replaced with a single admittance. Okay, you can write in admittance, let's say you have a parallel circuit y1, y2 and y3 until yn, for example. You can write total admittance equal to summation of y1, y2 and yn. Okay, this is the equivalent admittance. Okay, this is the equivalent admittance y. Okay, for parallel y1, y2 and y3. Let's say given z, you can convert from z to y first, and then you can calculate total y. Okay, okay, look at to the example 2. Okay, so how to calculate total impedance or equivalent impedance in parallel. Okay, let's say we given circuit R in parallel with C. This is a time domain circuit because C given is 100 microfarad. Determine the equivalent of the circuit at a frequency of 20 Hz. Okay, frequency 20 Hz. So first what you need to do actually is you need to convert from time domains to phasor domain. Okay, how to convert R, which is become ZR. Okay, ZR equal to 800 ohms. Okay, which is equal to R. ZC, how to determine ZC? Given C equal to 100 microfarad, your ZC equal to 1 over J omega C. 1 over J omega C, frequency is given, omega equal to 2 pi f, and you get ZC. So, Z equivalent equal to R in parallel with ZC. Okay, R in parallel with ZC. Let's say we call it this, this is a, let's say this is a ZR, this is a ZC. So 1 over Z equal to 1 over ZR plus 1 over ZC. In this case, I write Z1 and Z2. Z1 equal to R, ZR, Z2 equal to ZC. Okay, so total Z equal to Z1 times Z2 equal to Z1 plus divided by Z1 plus Z2. Okay, equal to this one. Okay, or you can write, or you can directly use your calculator. Okay, for example, in bracket 800 inverse plus in bracket minus J 79.58, close your bracket inverse. Okay, then you punch answer, and then you inverse that answer again. Okay, and then you will get this number. Okay, so hopefully you know lah how to use your calculator. No need to write Z1 times Z2 over Z1 plus Z2 lah. It's waste your time. This one is okay lah for the fundamental. If in the real circuit analysis, we just punch our calculator. We just use our calculator directly, to determine the parallel or to determine the equivalent impedance of the parallel circuit. Okay, So next, example 3, let's say determine the total impedance of the circuit at a frequency of 400 Hz. Okay, let's say we have a C 200 microfarad, we have a R, we have a L. This is a time domain because L given in 1 milli, not given in ohms. Okay, C given in farad. Okay, so convert to the phasor domain. First of all, you need to convert to phasor domain. Okay, let's say I assume Z1 equal to ZC equal to 1 over J omega C. Okay, J omega C, and Z2 let's say equal to R plus J XL. Okay, in series so we just plus R plus J omega L. Okay, so our Z2 equal to this one by using your calculator. This is Z2. So in this case, what is the total impedance seen from here? Okay, it shows that ZC, it shows that Z1 parallel with Z2, right? Z1 parallel with Z2. So you can use your calculator because 1 over Z equal to 1 over Z1 plus 1 over Z2. Okay, so you can use your calculator, Z1 inverse plus Z2 inverse. Answer, then you inverse again, you can get Z. Okay, this is the total impedance. Okay, look at to the next example. Okay, determine the input impedance. This is the input impedance of the circuit at omega equal to 10 radian per second. Okay, omega equal to 10 radian per second. Okay, this is the time domain circuit. Okay, because C in millifarad, L into Henry. First of all, what you need to do, convert from time domain to phasor domain or to frequency domain. Okay, so let's say you assume this one is, because this one is in series. Okay, so you can call it this one as a Z1, combination of C, ZC and ZR. Okay, so your Z1 equal to 20 plus 1 over J omega C. Okay, 1 over J omega C. Okay, you can use your calculator and then you can get this one. This is a Z1. Okay, Z2, let's say because this one is in series is very easy to calculate. It's just a sum between R and C or R and L. Okay, this one this is our Z2 equal to ZC equal to 1 over J omega C. This is our Z2. This is our Z2. And Z3 basically is series combination of L and R. Okay, so 50 plus J omega L. Okay, plus J omega L equal to this one. Okay, so what happened to your equivalent circuit? So you have a Z1, you have a Z2, this is a Z2, and then you have a Z3. So can you imagine Z2 and Z3 are in parallel? Okay, so and then in series with Z1. So total Z, total equivalent impedance or total impedance, okay, equal to Z1 plus Z2 in parallel with Z3. Okay, is it clear? Z1 plus this one Z2 in parallel with Z3. Okay, so you solve for Z1 in parallel with Z2 in parallel with Z3 first, and then you plus Z1. Okay, how to solve this parallel Z2 and Z3? You can use this equation. Okay, Z2 times Z3 divided by Z2 plus Z3, or you can directly use your calculator. Z2 inverse plus Z3 inverse, answer, and then you inverse again, and then you plus this Z1. So you can directly get this answer. Okay, this is the baby step solution. Okay, clear? If you don't know how to use your calculator, okay, you can ask me in WhatsApp group. Okay. Okay, I hope you really understand this example. Okay, next look at to the exercise. This exercise number 1. Okay, you can try this. You can try to solve this exercise. Okay, let's say I try to explain in brief. Determine the input impedance. This is the Z, input impedance Z of the circuit at frequency of 220 Hz. Okay, given C, L, R, and this one combination R and C. Okay, so first of all, what you need to do, you need to convert to phasor domain. This one you can combine. This one you can combine. Okay, this one you can combine. Okay, let's say this is your Z1. Okay, this is your Z1. This is your Z2. Combination of ZR plus and okay ZC. ZR plus ZC become your Z2, and then this is your Z3, ZR plus ZL. Okay, and then this Z3 in parallel with Z2 and in series with Z1. So you can write Z1 plus in bracket Z2 in parallel with Z3, and then you can solve for input impedance. Okay, next subtopic. So this one you can try by your own. Okay, next this is the most important part in AC circuit analysis, and we call it a phasor analysis. Okay, the steps of phasor analysis. Okay, phasor analysis. Okay, phasor analysis, or we call it a steady state analysis. Steady state AC analysis consists basically of 4 steps. Okay, first of all, what you need to do, you need to transform all the source, all the impedance sources to the phasor. Okay, let's say maybe your source given in time domain, you need to transfer to the phasor. Okay, we already discussed in the previous chapter. Okay, number 2, calculate the impedance of the passive element. You need to calculate the Z of each element. And number 3, apply analysis method that you already learned in electric circuit analysis 1, or you just apply, which is what is the meaning of this one? You need to apply Kirchhoff voltage law, Kirchhoff current law, KVL, KCL, and Ohm's law, okay, to the AC circuit analysis. And then apply inverse phasor transform to time domain. Let's say the question asks you to determine the time domain first, then you need to transform back to the time domain, from phasor to time domain, expression for currents and voltage of interest if required. So in phasor analysis, we have to bear in mind, we have to remember, or we have to understand that all the sources must have the same frequency. If we have the source with the same frequency, so we can apply phasor concept. Okay, look at to the example. Let's say we have a circuit. Okay, this is a time domain circuit. Let's say given voltage supply equal to 35 cos omega t plus phase angle. This is a voltage source, Vt, small Vt, small Vs, T. Okay, R, C, and L. This is a time domain circuit. First of all, what you need to do, you need to transform from time domain to phasor domain, or to frequency domain. Okay, determine so question number A, determine the angular frequency of the system. What is the angular frequency? Okay, omega. Angular frequency equal to omega. In this case, omega equal to 1000. Okay, this is omega t. Okay, B, impedance of R in ohms. Impedance of R in ohms. What is the impedance of R in ohms? Equal to 50 ohms. Okay. Number 3, C, impedance of L in ohms. Let's say we have a L. We have a L equal to 25 millihenry. So what is the ZL? Equal to J omega L. ZL equal to J omega L. And ZC equal to 1 over J omega C. And this one you need to remember. Okay, for ZL and ZC. ZC equal to 1 over J omega C. So 1 over J equal to minus J, equal to 100 ohms, for example. Then you can redraw your phasor circuit, phasor domain circuit. Okay. So what is the total impedance? Total impedance actually is summation of ZR plus ZC plus ZL. Okay, and then you can get your Z total Z or Z input, Z seen from the input. Okay, so find the phasor voltage and current. Okay, voltage supply, okay, you can convert from time domain to phasor domain. Okay, 35 angle 30 degree volt. Okay, from the time domain equation you convert to phasor domain. Okay, so you have a Z, so you have a Z in, you already calculate total Z. You have a Vs, so you can determine current by using Ohm's law or Kirchhoff voltage law. Let's say you apply Kirchhoff voltage law, minus Vs, okay, plus, okay, minus, okay, Z in times I. So so by solving this equation, I equal to Vs over Z in. Or in other words, you can apply Ohm's law, because voltage across voltage Vs equal to voltage across Z Vs. So I equal to Vs divided by Z in. Okay, this is in polar form or in frequency domain. So the question actually asks you to write in time domain. So you can convert this one from polar form to time domain. Okay, IT equal to this one, cos omega actually is equal to 1000. Okay, this is an angle. Okay, angle equal to this angle, this is the magnitude. Okay, is it clear? And then the next question, find the voltage across inductor. Let's say the question asks you to determine voltage across inductor. So we have a current here. So current through the L, C and R actually is equal to this current, equal to this I. So VL equal to I times ZL, I times ZL, and then you can get VL. Okay, you can get VL. Okay, let's say you have a I, and then you have a VL. So how to draw the phasor diagram? This is the important part. Okay, draw the phasor diagram. You have a I. Okay, this is phasor diagram. What you need to do, this is a okay, horizontal axis, vertical axis. Okay, this is start from 0, angle 90, okay, 180, 270, and go back to the 0 point or equal to 360. This is the rotation of the phasor diagram. Okay, from 0 to 360. Okay, for current you have a 0.388 angle 86.31. This is the position, 86.31. You just estimate lah. Okay, just estimate. Okay, for Vs 35 angle 30. Okay, this is angle 30. This is angle 30. So okay, this is the way how to draw, how to sketch your phasor diagram. Okay, this is the important part. Okay, after you calculate the voltage, current, and then you need to know how to draw the phasor diagram. So from this current and voltage, what we can conclude, for this circuit, current leads voltage. Okay, current leads voltage, mendahului voltage. Sebanyak berapa degree? 86.31 minus 30 equal to 56.31 degree, which means that current leads voltage by 50.31 degree. Or in other words, we can say that Vs voltage lags mengekor current by 50.31 degrees. Okay, is it clear? Okay, next example 6. Okay, based on the circuit below, determine the Vt and It. Okay, given in time domain, so you need to convert to phasor domain. Okay, Vs convert to the phasor domain, and then XL you can convert to phasor domain, equal to ZL equal to J omega L. Okay, JXL. So you can determine the total or equivalent impedance seen from the source, which is equal to 4 plus J2, 4 plus J2 in series connection. This is in series connection, 4 plus J2. Okay, and then you can draw the phasor domain. You can draw the phasor domain. Okay, so from that you can determine current. By solving KVL, you can determine current, because current equal to KVL or Ohm's law, V over Z. You have a V divided by Z, you can get a current. Okay, find phasor voltage. Okay, phasor voltage drop across inductor. Okay, you have a current. How about the voltage drop of the across inductor? Voltage drop across the inductor. Okay, V equal to ZL times I. ZL times I. We have a ZL, and then you can times by current. So you can get the voltage. This is in polar form or in frequency domain. Okay, so from polar form, you can convert to the time domain, because your question asks you to calculate VT and IT. Okay, VT, what is VT? VT, voltage across inductor. IT, current through the inductor and R in series. So then you can convert back to the time domain for current and voltage. So this is a current, 1.12, 1.12. Okay, this one, 1.12, this one. Okay, 1.12. Okay, cos omega equal to, what is omega? Equal to 10. Okay, 10 is omega, and then this is an angle. Okay, similarly to voltage, this is a magnitude. This is a magnitude. And this is angle. So you can get your IT and VT in time, voltage and current in time domain. Okay, so next, example 7. Okay, find the steady state expression for V0. Where is V0? So voltage across L, for example. If VG or generator or VGT equal to this one. Okay, find voltage across V0. Can you determine voltage across V0? Okay, yeah. Okay, so convert from time domain circuit to phasor domain circuit with omega equal to 8,000 radian per second. ZR, ZL, and ZC. You determine ZR, ZL, and ZC. ZC, ZR, and ZL. And then you can determine total Z, total impedance, okay, seen from the input, okay, which is ZL parallel with ZR, okay, or ZR parallel with ZL, and then in series with ZC. So ZC plus ZR in parallel with ZL, okay, which is, and then you solve for parallel of ZR and ZL. 2000 inverse plus J 4500 inverse answer, and then you inverse again, and then you plus this one, and then you can get this answer. Okay, that's the faster way lah, how to determine impedance in parallel. Okay, oh yeah. Okay, then find the phasor voltage and current. Okay, given VG equal to 64 angle 0, and then you can determine current. Current equal to, by solving this law, okay, this is your equivalent circuit frequency form, in phasor form. Okay, I equal to VG over Z in, you can get current, and voltage drop VL across inductor. Where is the position? This is the voltage. So the question asks you to determine voltage drop across inductor, which is equal to voltage drop here at this point. Okay, this is a same node now. We have a same node. Okay, this node, let's say node A, and this is a node B. So you need to determine the combination of Z between ZR and ZL. Okay, so voltage here, we need to determine how to determine voltage drop VL across inductor. V0 equal to Z times I. This is, we have a current here, times by Z, combination of ZL and ZR. Okay, because voltage across ZL equal to voltage across ZR, which is equal to voltage across combination of ZR and ZL. So Z equal to ZR parallel with ZL. By using calculator, you can determine this one and then times with current, then you can get voltage. Okay, in polar form, then you can convert to the time domain. Okay, then you can convert to time domain. Okay, from polar form you can convert to time domain, same magnitude, same phase angle, and then same frequency, angular frequency. Okay, we use a cos. Okay, clear? Okay. So last part, concept of reference phasor. When no reference angle is given either for the supply voltage or the supply current, we can define our own reference angle. So how to define the reference angle if there is no reference given for voltage and current of the supply? Okay, the following examples show the use of reference phasor concept in AC circuit analysis. Okay, look at the example number 8. We have an AC circuit consists of R in series with a C connected across 200 volt 50 Hz supply. Okay, we have a source connected to R and C. Okay, the supply voltage equal to 240 volt and 50 frequency, 50 Hz frequency. What is the meaning of 240 volt? Is it RMS value or peak value? Because there is no information of current of angle given in this question. Okay, this is the RMS value. This is okay because this is the frequency. Okay, commonly information given with frequency basically is the RMS, not the amplitude. Okay, so sketch the circuit and calculate the current in the circuit and its phase angle relative to the supply voltage. Okay, sketch the circuit first. We have a Vs connected in series with R and C. Okay, phasor domain. So first of all, for the source given 240 volt 50 Hz, you need to determine the peak value. What is the peak value of this source? Okay, we know that we have a peak, we have a RMS. This is, let's say we have a sine wave. This is the review. Let's say you have a sine wave. Okay, this is a peak or maximum point. Okay, this is the RMS value. What is the relationship between peak and RMS value? This one you have to remember or you have to understand. Okay, so the peak or maximum point equal to square root 2 times VRMS. Square root 2 times VRMS. In this case, given VRMS, so we can determine V peak. So we can determine V peak by times with the square root 2. So angle is not given. Okay, point number 1 done. Point number 2, if there is no information of the phase angle of the supply, so we can assume that our supply, the phase angle of the supply equal to 0 as a reference. We can choose as a 0. Okay, by assigning an angle to the supply voltage phasor, it means that we have chosen it to be reference. It's become a reference phasor, and the angles of other phasor in the circuit are measured with respect to this angle of the supply voltage. Okay, so then you need to determine impedance. Okay, from the circuit, phasor circuit, you can determine the impedance ZC. Z total equal to ZR plus ZC. Okay, ZC equal to 1 over J omega C, and then you can use this one. This one equal to ohms. Okay, don't forget to write the unit ohms. And then the supply current. Okay, the supply current equal to, by solving the Ohm's law or Kirchhoff voltage law, I equal to Vs over Z. Okay, V. Okay, please bear in mind this V basically actually is the magnitude actually is peak, peak value. That's why we need to times with square root 2. Angle 0 divided by Z, and then you can get current. direct current. So in time domain of the current, you can convert from polar form to time domain. Okay, is it clear? Okay, let's say next, you need to draw the phasor diagram of current and voltage, for example. Okay, so given voltage, angle 0 as a reference. This is a voltage, Vs, angle 0 as a reference, and your current equal to angle 4.07, for example, 4.069, angle 72.56 with angle of 72.56. This is a position. Okay, you just estimate, you just sketch the phasor diagram, and this is your current. So this current basically is the position of current, the angle of current basically is refer to the angle of Vs. So in this case, what we can conclude actually is I leads voltage Vs by 72.56 degree. Okay, this current leads supply voltage by 72.56. Leads, mendahului. Okay, or in other words, you can write Vs lags. Vs mengekor. Kalau I mendahului, yang mengekornya siapa? Vs. Okay, so in other words, you can write Vs lags current by 72.56. Okay, this is important. Then you have to understand this concept. Okay, so next, okay, this is our last example. I think this one you can try by your own. Okay, this example become your exercise. Okay, let's say I will explain in brief about this example or this exercise. Example 9. Let's say we have a resistor 10 ohms is connected with series capacitor 120 microfarad across 20 volt 100 Hz frequency. When we have this information, please bear in mind, please remember, we have information across a 20 volt 100 frequency. Given voltage and frequency, it means that this one actually is a RMS value, not peak value. So VRMS. So you need to determine peak value. Okay, in your analysis you need to use peak value. So you convert from RMS to the peak value. Okay, so calculate impedance of the circuit. You have this one in series. Okay, you can determine ZR, ZC, and then summation of ZR and ZC becomes your impedance, total impedance. And determine current. How to determine current? You can solve by using KVL, and then you can get current. And then the last one, calculate the voltage drop across each component. Okay, voltage drop of component R equal to VR, component C equal to VC, and you have a current I across R, I through the R equal to I through the C. So VR equal to IR, VC equal to ZC times I. Okay, so that's all for this example. Okay, please try by your own. Okay, so I think that's all for today. So thank you very much. Okay, Assalamualaikum warahmatullahi taala wabarakatuh.